comes in your mind. Yes, Parth, that's correct. Raj, not right. I hope you guys are not trying this, finding out force because of each of the four charges. If you're doing it, you're wasting your time. Force that can,
Sir, are there only 4 charges or 5?
yes, there are four charges only.
Okay, sir.
Plus Q, plus Q, plus Q, plus Q. So are you guys finding out force because of this in this direction, force because of this in this direction, because of this in this direction, because
No,
of this?
sir. Just cancelling out two opposite
Nope.
charges.
It's not a square. This is not diagonally opposite to it. These are not cancelling out also. No, Parth, that is not correct. So guys, this is method one, which is really lengthy. We are not going to use it. We'll use the second method. And this is a method which is used for JEE in grade 11th also, in grade 12th also. In a number of chapters you have used it. That is the method, not principle. Guys, there's a difference. We are using the method of superposition. Some people get confused with it. Some people confuse it with principle of superposition. Do you know the difference? Principle of superposition. Principle of superposition says that like any vector, it is actually true for. This is true for all vectors. It says net electric field is E1 vector plus E2 vector plus E3 vector. You can do it with forces also. Any force vector is addition of all these. This is called principle of superposition, which is like very obvious. Any vector is sum of other forces, other vectors. Method of superposition is different. This is like what we use in 11th and 12th JEE number of questions as a trick. What it says is assume there are charges on all four corners of it. See how simply this can be done using it. You will assume there are charges on all, sorry, not four, all the five corners of it, which is not even the question. Let's imagine plus Q, plus Q, plus Q, plus Q, plus Q on all five vertices. Okay, and a charge plus capital Q at the center. What will be the net charge in this case? Of course, this is not the original question, but what will be the net force in this case? Yeah, in this case, net force will be 0. Why? Are they cancelling out? Actually, there's symmetry in all five sides. So that is why they will cancel. Now what we'll do is we will superpose over it another setup. Remember, like while using the center of finding the center of mass also of with cavity, we used to do this. First consider positive mass, then consider negative mass. So here what we are going to do is instead of plus Q, now we will assume there is a charge minus Q and this positive Q at the center. So what will be the force on this charge if charge minus Q was present over here? Can we say force, attractive force will be present over here? And that will be K into capital Q small q divided by this distance, which is L square. Do you guys understand this? So because of this, it's 0, correct? Yeah, that's great, Neil. Yeah. And because of this, it will be this much. So if I superpose over it, won't it give me the original setup with no charge present here? Plus Q minus Q becomes 0. And so the net force is also this one, 0 plus this KQQ by L square in the towards the empty corner. And that's the answer. Okay, remember this trick. This will be used in a number of chapters, as I mentioned. In 11th also, we have used it at a number of places. In 12th also, we have used and we will use also. In the rest of the, in our term 2 portion also, which we'll cover after term 1, there also will be using this trick a number of times. But Varun, in the wrong way, will get the different answer. No, Varun, we will get the exact same answer. In fact, see, vectorially also you can say net force is actually in this direction towards the fourth one. We will get the same answer. If we go for the lengthy approach, how would you use it? If we go with that, then it's going to be tricky, like not tricky, it will be lengthy. You will have to find out, first of all, each of these angles in pentagon that you can do using geometry. This angle you will find. Then you will have to find this. Forces are easy to find, but the problem is the angles between them. One force is this, another is this, another is this, another is this. Okay, so, and this is the direction in which, because of symmetry, the net force will be. So first you will have to find this angle, whatever that is, then this angle, then this angle, then this angle. You'll have to add their cos components. F cos theta 1, F cos theta 2, F cos theta 1 on the other side, F cos theta 2. That will give the answer. Very lengthy. But is that fine? Okay. So with this, can we move to the next question? Okay. So the next question that we have is, like, I'll be majorly focusing on questions which are either very common for J or some tricks are there in it. Do you remember this for the case of a finitely long charged wire? Like we used to say, if it's a finitely long charged wire, and if I consider a point P over here at a distance R from this wire, the angle at the top is alpha, angle at the bottom is beta. Alpha, beta. If you feel like I'm going a bit fast, let me know. You can always ask doubts. I will slow down. So what is the electric field at point P? What was the formula for this? Like, we can derive it easily, but it will take a little bit time. So that is why we have learned it. There were two cases for it, like two different components were there for this electric field. One was the component of it along x-axis. So along x-axis, the electric field was lambda upon 2 pi epsilon naught r sine alpha plus sine beta divided by 2. Do you guys remember this? This much is the rightward electric field because of it. When we used to put for infinitely long, it would be used to become sine alpha plus sine beta divided by 2 was 1. So infinitely long charged wires, lambda upon 2 epsilon naught r. Fine, easy to remember. And similarly, downward one was what? Ey equals to lambda upon 2 pi epsilon naught r cos alpha minus cos beta divided by 2. This was the formula for vertical one. If it's positive, negative, that you can check depending upon how the wire is. Right. Okay. Let's do a simple question first of all on this. If I say there's a wire like this, this is the point P where you're supposed to find the electric field. Charge point length is lambda. This angle is 60 degree. To be able to use these formulae, what's the value of alpha, guys, in this? Beta's value. And if I say this distance is r naught, what's the value of the distance r in this denominator? Tell me the value of each of them. What would you substitute in these formulae? Correct, Prithvi. Correct, Dhruvi. Yes, Atharva, correct. Akshat, correct. Yeah, I guess everyone is correct. Yeah, guys, correct. So the angle that the topmost point forms with this axis, this line joining it, is 60 degree. The angle that the bottommost point forms with it is actually 0 degree. And the value of r, the perpendicular distance is r naught. That is the answer. Okay. But what if the question was something like this? This is the point P that we are supposed to find the electric field on. It's given to be plus lambda and the angle that it forms. This distance between this wire and this point P is given as R naught. This angle is 45 degrees. And the angle at the top is this one. Total angle is 60 degree. So what's the value of angle alpha, angle beta, and the distance? No, Akshat, that's not correct. Dev, good, that's correct. Yeah, Shashank, that's true. Nihir, not right. Bhumi, yeah, this part is correct, Bhumi. Vedant, good, that's correct. Varun, that's not right. Atharv, correct. Pranshu, correct. Parth, not correct. Rahul, not, yeah, Rahul, that's correct. Dhara, correct. Rahul, yeah, correct. Latika, not right. Abhinraj, not correct. Washir, what have you written? Acha, no, this is not correct, Washir. Lehri, no, that's not right. No, Varun, not right. Okay, now I'm getting so many messages. I'm not able to cope up now. Let's see what the value is. Alpha over here. Alpha is the angle that the topmost point, the tip of this, forms at point P. But what is the other line that it forms this angle with? Look at the original figure. Alpha is the angle the line joining topmost point to this point forms with the dropped perpendicular. What is the line perpendicular to this? Is this gray line represented by this R naught? No, that is not the angle that we're talking about. We're talking about this one only. This is the perpendicular dropped to this line. Okay, so necessarily it has to be this angle 60 degree with this pink line. If I talk about beta, what's the value beta? Is it 45 only? Now most of you have written it 45. It's not 45. Look at this. Beta is the angle, though beta is the angle, bottommost point forms with this perpendicular drop, which looks 45 only. But see, when we have derived this formula, we have considered that beta is the angle below this axis. So if by chance the angle beta is above the axis, you need to substitute it with minus 45 degrees. Otherwise, it will be wrong. Otherwise, this formula will not work. And if you're talking about R is the perpendicular distance, which is this distance. R not cos 45 degrees. Let me know if you have any doubt, got any doubt in this. Shashank, because beta is the angle that this line forms with this perpendicular below it. Okay. Yes, Abhinraj. Yeah, that's correct. Hmm. Okay, Mubashir. Fine then. Okay. So let's move to the next question then. If you feel like I'm going a bit fast, please let me know. I'll slow down the speed accordingly. Can you try this question? It's quarter of a circle, and this circle is having radius r, and the length of this part is 2r. It is charged uniformly everywhere. So I guess you guys already know what is being asked. Electric field at the center of this question mark. Like it looks like a question mark, that's why. So what's the electric field over here? It's given charge per unit length is positive lambda. Mihir, this is the answer for the previous question. How about this one? No, it doesn't seem correct. Should be a bit different. You're saying small r equals to 0. Okay, no. Dhara, that formula is not valid over here. That formula is valid only if a point is at a certain distance from it already. If r is exactly equal to 0, you need to derive for it. No, Aryan. If it was a current carrying wire, then at this point you can say magnetic field was 0, but not electric field in this case. Electric field does exist along the axial point. Okay, Bhumi, yeah, same thing. Pranchu. Is this the net electric field, Pranchu? I don't know. Doesn't seem correct. I see. These are two different concepts over here. One is electric field due to circular arc. Okay, Nigiri, okay, I'll give you 1 more minute time, guys. Take your time and then we'll discuss it. Okay, Parth. Let's see. Now I'll have to calculate. I don't know. Okay, Rakshita. Uh, let's see. I'll calculate and then I'll be able to tell. No, Brittany, this definitely is not correct. So this is the concept of electric field due to charged circular arc. This is composed of two different questions. Another is electric field due to charged wire at an axial point. So we need to derive it in general for both the cases. Like we have the circular arc. Let's say it subtends an angle theta at the center. Remember this? Like this was covered in class also. This is the angle alpha. Charge per unit length is given as lambda. Let's say. Okay, let me draw it properly now. Plus lambda. The radius of this ring is given as capital R. And you guys are supposed to find the electric field at its center. So how can we actually find this? Let me change this color. Using the concept, yes, using integration, you can do it, right, guys? What you can do is you can draw a line because the elements are basically along an arc, they are circular. So you also need to use polar coordinates for this question. Using polar coordinates, like you will take a reference line. With respect to this line, you're going to consider an element at an angle theta. At an angle theta, let's say over here, I consider a very thin element like this. Basically, my element is this one. So I have taken an element at this angle theta, subtending an angle, very small angle d theta at the center. So what is the length of this element going to be equal to? What's this length dl equal to? Yes, r d theta, because radius is r, angle subtended is d theta. So what's going to be the charge which it carries? dq. That is going to be charge per unit length multiplied by its length dl. That's lambda r d theta. This is the charge. So this red charge which is present over here is going to produce an electric field at this point, dE, very small electric field because of very small charge. So what's the value of that electric field? That's K into small charge dq divided by distance. What's the distance between charge in this point? Correct, Neil. Capital R square. Good. So this is the small electric field. So can I say once I found the electric field, I can find out the net electric field integrating it. Like net electric field is integration of all these small d's. Can I say that's correct? Okay. Yeah. That is actually not correct. What's wrong about this? You can add magnitudes of vectors only if vectors are in same direction. Like if you have 2 Newton force towards right, 4 Newton force towards right. What's the net force? 6 Newton. You can add 2 and 4. Why? Because they're in same direction. But what if 2 Newton was upwards, 6 Newton was upwards? Can I say net force is 8 Newton here? No. So you cannot add vectors. You cannot integrate if they're in different directions. You can only add their components. But from symmetry, I know in this case, certainly horizontal components cancel out each other. Horizontal components cancel out. So from this, I can say not the horizontal, but verticals I can definitely add. So what we'll do is we'll say this angle is theta. So this angle also is theta. So d cos theta can be integrated. Is this correct? Yeah, this is right. So now you're going to integrate it very simply. That is like integration k dq by r square cos theta. Okay, dq you know is lambda r d theta. You'll bring the things out, t lambda by r integration cos theta d theta. What will be the limits of integration in this case? From where to where does theta vary? Theta is the angle this line makes with the vertical. So the farthest on the right is positive alpha by 2, half alpha on the right side. And the smallest possible value is on the other side minus lambda by 2. So limits of integration is plus lambda by minus lambda by 2 to plus lambda by 2, and you get 2k lambda 2k lambda by r sine alpha by 2. This formula you need to derive. I do not suggest learning this. Not a very common one, but if it is the question is asked, we can see derive it very quickly. Here we have explained it everything over here, but by yourself you can do it within 1 minute. Okay, so this formula is for a charged circular arc. So that is basically one half of the question. It's a charged circular arc where alpha is equal to what, guys? What's the value of alpha here? Yeah, great. 135, yeah, 180 plus, no, it's 270, no? Yeah, 270 or 135. Yeah, 3 pi by 4, or you can say, guys. So you can substitute alpha over here and then you might be able to get some answer. Okay, let's not go into that trigonometry part. Okay, okay. Yeah, Aryan is asking for 2R is similar to gravity, 1 L plus R for 1 minute will do that. Yes, exactly, Aryan. That's true. So guys, for the other one, if you see, this is a linear charge distribution. It's like a rod having some length L at a distance R from this point P. So can you guys now find out the electric field at point P because of this charge rod? Try this derivation quickly. Ah, 3 pi by, sorry, yeah, guys, I'm so sorry. It was 3 pi by 2. It will become 3 pi by 4 after dividing. Yeah, L by 3 pi by 2. Acha, Nihit, this is the final answer after putting in the values for the second one. Okay. For the values. No, I don't think that's correct. Oh, okay. That's right. Yeah, Nihit, you're correct. Lambda minus 1. What do you mean, Bhumi? I am not, like, can you put brackets here? I'm not able to understand your answer. Yes, Ansh, that's correct. Good. Aryan. That's correct. Correct, Aryan. Yes, Atharv, correct. Okay, so guys, let's quickly do this derivation now. Again, we'll do the same thing. Every time we have a mass distribution or charge distribution, here we have charge distribution, electrostatics. So we will consider small charges. We'll differentiate it into small pieces. Let's consider this piece. We're considering this at a distance x from this point, having length dx. So what is its total small charge going to be? Small charge dq is going to be charge per unit length multiplied by its length. Everyone clear about this? Charge per unit length multiplied by its length. So because of this red element, there is going to be a red electric field at the left side, like on the left side, sorry, directed towards left at this point. This small electric field because of this charge is going to be what? Charge is dq, distance is x. So it's going to be k dq divided by x square, right? Can I say I can find net electric field by integrating this? Can I say that's correct? Here also electric field is vector quantity. Can I integrate small electric fields and get the total electric field? Why or why not? Yeah, we can do that because these are in same direction. Had I considered any other element also, for example, I considered green. Because of this charge, what will the direction of electric field at point P? That will be again towards left D. So because all of them are in same direction, we can use it. Since all DE are in same direction. That is why you can integrate it. That is why you were not able to integrate in the left part. This part of it. So that's going to become k dq by x square. That is integration k lambda dx divided by x square. What will be the limits of integration for this? From where to where does x vary? This distance x. The closest points distance is r. The farthest one is L plus R. So yes, it's going to be R to L plus R as you guys have written in the chart also, correct? So it's going to be K lambda 1 by R minus 1 by L plus R. Okay, so you get some answer through this. K lambda L upon R plus L. That's the net electric field. So I think I do not need to solve this further. You can find its value easily now. Because of this, you can find electric field. Because of the circular ring, it's present here. Because of this rod, it's present on the left. So you can find its resultant very easily. Okay, these are the two formulas that are supposed to be used. You should realize that. Okay, anyone with any doubt in this? Fine. Next question that we can consider is from Gauss law. What did Gauss law used to say? Gauss law said flux through any closed surface is cyclic integral E dot dA. Cyclic integral means over closed surface we are considering this. This is charge enclosed inside that surface divided by epsilon naught. That is what we have here. This is what Gauss law used to say. Right. So on the basis of it, can you try this question? If I consider a hemisphere, and this is not it, there's another hemisphere below this also. Okay, like these are two hemispheres facing each other. One is having radius r, another is having radius 2r. Both have the common center. If I place a charge over here, plus q, at a distance r by 2 from its center. So find total flux passing through curved surface of the hemispheres. This distance is r by 2, guys, the red distance. Yes, Dave, that's correct. Yes, Rakshita, correct. Yes, Pranshu, correct. No, Dhara, that's not right. No, Ansh, not correct. Nihir, that's right. Atharv, that's correct. Yes, Pranshu, that's correct. True. Because realize, where did Gauss law come from, Pranshu? Guys, Pranchu is asking if the material of the medium changes, if it's not vacuum anymore, will we have the formula of Gauss law Q upon epsilon? What do you guys think? Yes, it's true. Because where was this formula derived from? It was derived from Coulomb's law only. In fact, if you like do it for a point charge, won't you get E into 4 pi r square is equal to Q upon epsilon naught? So electric field is KQ by r square, the same thing. So yeah, it should be epsilon in that case instead of epsilon naught. Yeah, guys, now let me discuss this. It's a very easy question. Answer is Q upon epsilon naught. Let's see how. It doesn't matter what the shape is. All these things do not matter. How is the charge going to create its electric field? That we should be able to visualize. We should not always get stuck with the math in this problem. Imagine how electric field lines are coming out. Won't they come out symmetrically only without any change? Like this. Electric field lines will come out like this. Correct? Had this charge been placed in a closed sphere, let's say at the center, how will the electric field lines look like in that case? Exactly the same way. What exactly is flux? What does it measure? Flux is a measure of number of field lines passing. It gives you an idea how many field lines are passing. If there is one surface which has half the electric field, it will have half the number of field lines passing. So half will be its flux also. So over here, whatever field lines are passing through this sphere, can I say, had the charge been placed not at its center, wouldn't it still have the exact same number of field lines passing through this? Although not from the same locations, but total flux or total number of field lines passing will be exactly same. If 8 field lines are passing through the left one, 8 are passing through the right one also. If flux through the left one was Q upon epsilon naught, sorry, I should change the color. Yeah. If flux through the left one is Q upon epsilon naught, to the right one also should be Q upon epsilon naught. Do you guys agree with that? Anyone with any doubt in this? Okay. So can I say whatever field lines are passing through this will be the same passing through these two hemispheres also. So here also the answer is Q upon epsilon naught. Every field line that comes out of Q will eventually pass through this. In fact, had I asked this question, what is the flux passing separately through the top one and separately through the bottom one? What are their individual fluxes through their curved surface? Exactly, half. Because exact half field lines with the half field number of field lines pass through the above surface and half go at the bottom. So fluxes are going to be same. Okay. Yes, exactly, Aaron. Can you like easily do it for this case also? There's a hemisphere open at the bottom. There's a charge Q placed over here, a point just outside it. It is having radius R. So can you find the flux through its curved surface? Correct, Dara, correct, Rahul, correct, Mubashir, correct, other. Yes, Jerry, that's true. Yes, Abhinraj, Rovi, correct. No, Bhumi, that's not correct. Yes, Kid to right. Ansh, correct. Rakpita, not right. Rahul, correct. Prithvi, correct. Small, so for the smallest sphere, the flux through specific area close to the charge will be greater. Okay, if you're talking about flux, so what we're actually imagining over here is the flux density, right? Flux per unit area. Flux per unit area is the electric field, isn't it so? And electric field is larger at closer points. Okay, yeah, guys, here the answer is straightforward 0. Because again, don't do it mathematically, just visualize it first. What is the net number of field lines passing through this hemisphere? Can you imagine every field line that enters it is going to exit from the other side? We are supposed to remember this. Incoming field lines, incoming flux. Guys, incoming flux is positive or negative? Incoming flux in a closed surface. No, it's negative. Outgoing flux is positive. Here what happens is whatever number of field lines enter from left side, they go out of the other side, equally negative, equally positive, so total comes out to be 0. Yeah. So from this, can you try this question now? There's a hemisphere like this, the center, and electric field lines look like this. Electric field is uniform everywhere, and it is at an angle theta with this base of this hemisphere. This angle is theta, and the radius of this is given as r. So you're supposed to find flux through the curved surface. Are you giving this answer for this question? Ansh, then it's not correct. Yes, Aryan has given the right answer. Mihir, right, correct. Mubashir, correct. Atharv, correct. The direction is. So Dhruvi, it is given electric field is in such a way that with this face, the bottommost face, circular base of it, it forms an angle theta. No, Varun, that is not right. Dev, that's correct. Prachu, this is not correct. One mistake here, small mistake you're making in this, Prachu. Yeah, Abhin Raj, it is coming, like it doesn't even matter actually, Abhin. But yeah, fine, you can consider it coming from infinity. No, Varun, that's not right. This answer is not correct. Parth, correct. Good. Vedant, not correct. Small mistake, as I said. Ansh, small mistake is there. Dhruvi, that's correct. Ansh, that's not correct. Small mistake. Kittu, correct. Fine. Dhara, perfect. Yeah, Prithvi, correct. See guys, here what's the logic? Yeah. Let's talk about the net flux through this whole hemisphere. How much is it? Zero. Because it's a closed sphere. Every field line that enters from all this left side from which incoming flux is coming, exact same flux is going to go out of the other side. In 3 dimensions, of course, you have to visualize it, but same flux goes out of this side. So net flux is zero in this case. But this body is composed of two different parts. One is the top half, another is the bottom half. So we can say flux through the top plus flux through the bottom is equal to zero. Sorry, whatever it is. Flux through the top plus flux through the bottom is equal to zero. Basically, whatever is the flux through the upper half, exact negative of it should be the flux through the lower half. What are we supposed to find? We are supposed to find the flux through the top half, hemisphere, curved surface, which is possible to integrate and find, but very lengthy it will be. We don't want to integrate and find it every time. So what we'll do is instead we'll find the flux passing through the lower surface. This negative of flux passing through the bottom. Okay, so we'll consider this. We'll say electric field is passing like this. E is the area, electric field. And what's the value of area? Area is pi r square. But the most common mistake that people make, and some of you did make over here, is the angle. Electric field is E, area is A, but what's the angle between them? Angle between electric field and area was given as theta. But theta is not the angle between electric field and area. It's the angle between electric field and area vector. 90 minus theta. So that's minus EA sine theta. Flux to what? Flux to the top. Like I should not write minus. I'm so sorry, guys. I should be talking about magnitude. Actually, from the bottom, it's incoming. It is negative. Okay, let's talk only about the magnitude. Yeah, so the answer is EA sine theta. Okay, fine. On the basis of Gauss law, we used to find electric field because of different configurations, if you remember. For example, let's take the case of positive Q charge. So for this, we used to say, if you want to find electric field at a distance r, at this point, draw an imaginary Gaussian surface. We used to draw this imaginary Gaussian surface, and we used to consider electric field everywhere. From symmetry, it was same everywhere because spherically symmetric is the electric field. And we used to consider small area that its surface, dA, all these vectors, dA vectors. And then we used to say that flux, which is cyclic integral E dot dA is equal to charge enclosed upon epsilon naught. Then we used to say E into 4 pi small r square equals to Q upon epsilon naught. And that is how we use this Gauss law to find out electric field due to point charge. Similarly, you may recall, we used to do it for other cases also, like infinitely long charged wire was there. What kind of Gaussian surface did we used to take here? Since electric field lines were coming out cylindrically, yes, so we used to take cylindrical Gaussian surface here, like this. And then we used to do the calculation, cyclic integral E dot dA equals to charge enclosed upon epsilon naught. So E dot dA, like electric field is outward again, but area is the curved surface area of the cylinder. If we consider its height to be L, so E into curved surface area of cylinder 2 pi RL was charge enclosed. What's the charge enclosed inside this? Charge spinnet length is lambda, length is L. So it came out to be lambda L divided by epsilon naught. That gave us the answer. So electric field was lambda upon 2 pi epsilon naught R. And we were supposed to learn this result. Very common. Right? Then one more case we used to have. Infinitely large charge sheet. If charge density is plus sigma, what kind of Gaussian surface did we use to take here? What was the shape of the Gaussian surface from symmetry? Yeah, only two parallel sheets is important. Cylinder, cuboid, anything it can be. In fact, it can be of random shape also. But the main important point over here is two parallel surfaces should be there. If I have taken one point at a distance r on the right of any shape, exact parallel to it and to the sheet should be the other surface. Its shape could be anything. See, it's not even a cylinder here. If you made 4 corners, it will become a cuboid, and so on. The point is, if you consider this area to be A or dA, whatever you want, guys, you can take it. A, dA, your choice. So electric field here is E. On the left side also it was E. Area vector is always outwards. That is why on the left also it was leftward. And curved surface area has no flux. So cyclic integral E dot dA equals to charge enclosed upon epsilon naught. And from this we used to get 2 times EdA. 2 times EdA equals to charge enclosed sigma into dA divided by epsilon naught. So from this we used to get this answer, which we have very properly learned. This also we were supposed to learn. Okay, let's do a couple of questions on Gauss law. One very important case that we had considered when studying the theory was if there is a hollow shell or a conductor. Hollow shell basically meant that there is no charge inside it. Conductor also meant there is no charge inside it. Solid conductor hollow shell had same charge distribution, basically charged only on the surface. And it was very important from JEE's perspective. Most of the JEE main and JEE advanced questions from this topic are going to be based on this only. Sorry, if the radius of this shell is capital R, what is the electric field inside it and outside it? Using Gauss law, we used to find it. You might be able to recall. Yes, inside it was always 0 and outside it was like a point charge. If the charge, let's say, is capital Q, sorry, I forgot to write that. If I assume charge is capital Q, I consider a point outside at a distance smaller. It behaved like a point charge only. KQ by R square. This is also something that you need to learn from JEE's perspective. Okay. Then there was another case. If there was a solid charged insulator. Insulator means opposite to conductor, the charge is not going to move on surface. Let us consider uniform charge distribution. So here, charge is distribution on the entire volume. Charge, let's say, charge density, let's say, is rho. And a total charge also is given, let's say Q. Although, like, you can, if one is given, other you can find. But that is how we have in fact learned the result. Radius is R. So what is going to be the electric field inside and outside it, guys? Okay, Neil, you have learned it in this form. That is also fine. Okay, Rahul, fine. Like I have learned it this way. Like you can learn it in any way, it's your choice. But I find this one more helpful most of the times. Rho R by 3 epsilon naught for inside it and K Q by R square outside it. So for outside it always behaves like a point charge kept at the center as long as symmetry is there. Point charge kept at center, like whole charge is concentrated at center. And because gravitation and electrostatics follows the same maths, that is the reason we used to consider mass of the whole planet at the center. I wondered, law of gravitation was for point masses, but why do we consider it for a whole planet? And we used to say distance between the centers for the same reason. The whole planet behaves like mass is concentrated at its center only for points outside it. Okay, so here we can say point charge kept at center again. So why exactly are we learning these formulae? Where are they going to be used? So if you remember, there was one question in module. Okay, what exactly does it mean by conductor? Okay, insulator. See, Mubashir, what happens over here is, if I had taken an iron ball and I had given charges to it, can charges ever store inside it? Like if I assume iron is the best possible conductor, although it's not, but if it's the most ideal conductor, will charges stay inside it? No. Charges will, if I even give it charges inside, they will eventually move on the surface. So that is the first case I'm talking about, conductor. Charges always residing on surface. But if you want that charges should stay, even under electrostatic repulsion, you need to take maybe wood or plastic or any insulator, normal insulator only. So that charges which are given inside are not allowed to move. That is what insulator does not allow charges to move. So if they're stuck inside, they will be stuck inside. Okay, charge density will not change. Fine. The kind of questions which are asked in JEE, like this is one of the most basic questions. It's given in module also, you must have seen. Just a small recap. They're going to do something like this. One sphere they will take and they will say their density, the uniform charge density is given to this positive rho naught. And on this is superposed another sphere having negative charge density exactly the same, minus rho naught. I'm giving this because, guys, this was an old JEE advanced question. But now you know that is how JEE advanced does, that is what it does. It picks up an older question, keeps on making some interesting changes to it, and presents it as a new question. So now this is a JEE main question. And in future, JEE is going to change some of the concept in this and present it as a new question. Okay. So what we are supposed to what we'll be supposed to comment over here is comment upon electric field inside the overlapping region. What's the nature of it? Is it like uniform electric field, zero electric field? What exactly is the case? Let me give you three options: zero, uniform, non-uniform. No, Varun, that is not correct. No, Dhara, that is not right. No, yeah, charges are distributed uniformly, Ansh. That's true. Akshat, how is that so? No, they are not correct. It's like cavity. Zero derivation of solving. Yes, Aryan, that's true. But this won't be helpful actually here. Yes, Atharv correct, Nihir correct, and Varun correct. Rakshita not right. Harini not right. Aryan not correct. Ansh not correct. Prithvi not correct. Parth correct. Britney correct. Bhumi is correct. Zeal not correct. Rakshita correct. So guys, this analysis is very, very important. Yes, Dhruvi, that's right. Yes, Neil, exactly. That's right. Nasir correct, Pranchu correct. So see guys, what is going to happen over here is, this is how you're going to analyze these questions. This is to be done using vector. Because see guys, if you want to comment upon nature of any vector in entire space, of course you need to do it for a general quantity. And general analysis basically means vectors. You need to use vector quantity. Then only you'll be able to tell whatever you're finding is valid at only one point or at all points. If it's actually uniform everywhere or if it is not uniform everywhere. Getting it? Always try to do general analysis for these cases. Don't randomly consider the midpoint and start doing it. Go as much general as possible. This is one sphere, this is another sphere. If you guys are thinking that if these two charges these spheres overlap, this will have zero charge, the one at the center, right? That is what most of you thought. It does not help. In fact, you could have done the opposite. If the question was given like this, you would assume same positive and negative charge at both the places. So you are going to use superposition method for this again, like anti-superposition method, opposite of it. What we will do is, we will consider two centers C1 and C2. These are identical. I will consider this point P random general point over here P. And I will name this vector as R1 vector. So guys, what is going to be the electric field at point P? Electric field vector at point P because of the first sphere. Can I say it's rho naught R1 vector divided by 3 epsilon naught? Write it in the vector form so that you can comment upon direction also properly. Do you guys agree with this? Because it was positive, electric field was outwards. Outwards means in the direction of R1. And if I consider this as R2 vector, what's the electric field vector at point P due to second sphere in vector form? Yeah, correct. Minus rho naught R2 vector divided by 3 epsilon naught. right? Because it will be pulling electric field toward itself. It's a negative charge. So if I just vectorially add them, I'll get the net electric field. So what's the net electric field? Well, let's just add it. Let's not waste time. Rho naught by 3 epsilon naught R1 vector minus R2 vector. How does this formula tell if it's zero or uniform or non-uniform? What is its value, guys? Zero. R1 minus R2. Both rate distances are same. Yeah, it's not that. R1 minus vector, R2 vector, if you think about it vectorially, this vector minus this vector is basically the vector starting from C1 and going to C2. This C1, C2 vector. Rho naught by 3 epsilon naught. It is this constant C1, C2 vector. Neither is its magnitude changing, distance between centers, nor is its direction changing. Centers are fixed. So this is uniform. Answer is B. In fact, if you want to imagine how it would look like, actually you can do that now. See, what's the direction? C1 to C2 direction. Like whichever direction you are going to connect their centers, left to right, exact same is the direction of electric field in between them. What happens at other places is difficult to comment, but the overlapping region, we can certainly say it's like this. Okay, everyone clear about this? Fine. Let's move to the next concept. Next concept was electrostatic potential, if you remember. Right, simple questions you can do. If I give you 3-4 charges, you can add their potentials by pairing up. For example, if I take this Q1, Q2, Q3, Q4 on the vertices of a square. What's going to be the potential of the system? Assuming potential at infinite separation is zero. Potential energy, or you can say potential. Or let's say potential energy. Potential energy at infinity is zero. So what's the potential energy of the system? How do we do it? We're going to take pairs one by one. Like you will first of all find the energy of this charge's interaction with this charge, then with this charge, and then with this charge. Then interaction of Q2 with Q3. How many such pairs can you have over here, guys? How many pairs you can have if you are choosing 2 at a time out of 4? You're going to have 4 C2 pair, right? That is like 6. Yeah. So that's going to be find potential energy of 1, 2, 1, 3, 1, 4. 2, 3, 2, 4. And 3, 4. This will give the answer. You can find that KQ1 Q2 by L. That's the basic formula. KQ1 Q2 divided by L or R. R I should write. Okay, that is how we used to do these things. So can you guys tell me if this is the question? There's an infinitely large charge sheet. Sorry, plus sigma. Sigma is its charge density. And it's infinitely large, of course, otherwise you will not be able to solve questions, at least in the JEE syllabus. And I've taken one charge plus Q mass M, and it is given some speed. Let's say the speed given is in this direction, V naught. Okay, this V naught is in such a way that if I consider the perpendicular, it forms an angle theta with this. Okay, that is how it is. So guys, this V naught, so V naught is only in the XY plane. It's not in Z plane. So don't worry about that. Yep. X, Y, Z is outwards. So V naught is only in the XY plane. I hope you guys are able to visualize it. So you guys are supposed to find if I say that the original distance between them is D. And anything else I need to give? No. This sheet is fixed, nothing else. So you guys are supposed to find the minimum separation between them. Find minimum distance between charge and sheet. Mm, what, Mubashir? Which relation are you talking about here? For the above case, I don't know. Like, why would I never even thought that there's any formula behind it? Why do you need a formula? You want to learn as few things as possible. Learning is for chemistry. You don't need to get the answer. Just getting the equations will be fine. Of course, in the question in exam, they'll give the values. We don't need values right now. We just need equations. That is most important. So can you tell me which equations we are going to use? Energy conservation, Shashank says. Okay, of course, energy conservation is to be used. And no, Dev. In the beginning, this was fine, but later on, this went wrong. So, can you check? Final kinetic energy is the issue there. About which point, Nihir? So, Nihir says conservation of angular momentum. About which point? Yeah, Gladden, that's correct. But there's more to this. What is the next equation going to be? I am not able to understand this, K2. What have you written? How would I know which step you are actually on? MV square equals to this. No, Brancho, that's not correct. Incorrectly, you have used energy conservation. No, Dev. Incorrectly, you have used energy conservation here. No, 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 that's correct. Yeah, 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 Dev. That's correct. Good. V cos theta 110. That's true, K2. But what have you written here? D minus not md square cos. Oh, okay, okay, okay. D minus. Yeah, that's correct, too. Great. That's the correct equation. Equation of motion. Yes, Nihir, you can actually apply over here because constant force is there. True. Yeah, this answer is not correct, Nihir. Somewhere you went wrong in this. So guys, there are two, three ways of solving this question. Okay. Let's see. First of all, visualization is most important. How will this charge motion be? Can you imagine? There is a constant force towards right, because of which this is going to be the path that it follows. Just a second. It's going to go like this. It will feel a constant repulsion. But many of you imagine that it comes to rest here. No, that's not possible, guys. It is going to have some velocity when it is at this point. Do you guys agree with this? Some v1 velocity it is going to have, right? So when it is at the minimum separation, which is this R minimum, which we are supposed to find, it will have a speed v1. So two variables are present over here. One is R minimum, another is v1. Both are variables for us. We need to find both of them. So first equation is going to be conservation of energy. According to conservation of energy, you guys are right. Which energy is being lost? Which energy is being gained? Yes, Neil, correct. Kinetic energy is being lost and electrostatic potential energy is being gained. Correct. Gain in electrostatic potential energy equals to loss in kinetic energy. But just by seeing electrostatic potential energy, don't get your hopes high that you can use this formula kq1 q2 by r, that because that is for point charges. If you want to find out potential energy over here, you need to find the work done by this force. So what we are going to do is we will say constantly the force acting on this charge towards right, that is equal to charge multiplied by electric field, that is charge multiplied by sigma by 2 epsilon naught. Is that right? This is the constant force it is. And displacement towards left is d minus r minimum. Total distance was r, and now it is only r minus r minimum distance away. So total work done by this is going to be force multiplied by displacement. Let me write it this way. So this is equal to q sigma by 2 epsilon naught multiplied by d minus r minimum, and this is equal to loss in kinetic energy. Loss in kinetic energy is half m v naught square minus half m v1 square. Fine, we have got one equation, but we need one more because we do not know the value of v1. So how do we find v1's value, guys? Any suggestions? Hunch about which point? If you're thinking, guys, I have got this suggestion number of times now, conservation of angular momentum. About which point will you conserve it? I know which question you have in mind when you talk about conservation of angular momentum. You're talking about this question. Plus q, it was given a velocity, you are thinking it's going like this. Because there the problem, there the advantage was, there was a single point which was producing force. So torque about this point was always zero. So that's not present over here. We will use some normal logic. Correct, Athar. That's perfect. That's perfect. See, guys, in which direction is force acting? Force is horizontal only. Does vertical force ever act on it? No. Horizontal force only is acting. So that means that only the horizontal component can get changed. Originally, it was moving with v0 cos theta towards left. That became zero. But vertical, nobody is changing vertical component. So final vertical component, since force is horizontal only, we can say initial vertical force is equal to final vertical force. So initial vertical force was v0 sin theta, v0 at an angle theta. Finally, it is v1 only. So that's what we have got. So did you guys get this? Okay, you can substitute it in this and you can get the answer. Can anybody tell me any other method of doing this? Equations of motion, kind of yes. Like my other method is actually based on equations of motion only. Horizontal body, yeah, Ananya. See, what happens is force was always horizontal. Do you agree with that? This sheet was always applying rightward force. So horizontal force can always change horizontal momentum only. This particle, this blue particle, was moving towards left with v0 cos theta, moving upwards with v0 sin theta. So upwards it is always going to move with v0 sin theta only. So that's v1 equals to v0 sin theta. Yeah. Nobody has it in mind. I am surprised. Yes, Aryan, correct. No, Brancho, that's not going to help. Method 2 is projectile motion. Charge Q, mass M. Just rotate the whole setup by 90-degree clockwise. What is happening over here? Charge was thrown at an angle theta with this. Theta was the angle that it formed with this. Okay, no worries. This time this angle is theta. So what will be the motion of this particle? It's going to be parabolic. Got it? It was given original distance is d. And we are being asked the minimum distance. This distance we are being asked. No worries. We can find the h max. What's the formula for h max? H max is like u square sine square theta divided by 2g for this. Oh no, this time it's 90 minus theta. It's not theta, it's 90 minus theta, the other angle. And instead of g, what is the acceleration due to gravity over here, guys? What is the acceleration due to gravity g? You will have to find it this time. Correct. It's QE by m. Good. So just substitute it over here. You will get the answer. So minimum distance is d minus h max by substituting the appropriate values. You don't even need to solve any equation. Every time you see this infinitely large charge sheet, every time you're going to, like, whenever you see particles and charge moving like this, I always imagine projectile motion only. Okay. So somebody was asking, like, if we can do it using equations of motion. Yes, this was derived using equations of motion. So indirectly we are using that result. In the first method, you found potential using E equals to minus dV by dr. Yeah, that's also same. It's the same. Yeah, the electric field was uniform. So delta V equals to E delta X. That's correct. Okay, guys. After this, we can move to capacitor also. A couple of questions we can pick up from capacitor. So if you have any doubt in this question, let me know. Okay. Yeah. Couple of capacitors placed like this: 6 microfarad, 3 microfarad, 1 microfarad, 2 microfarad. And I use a potential of 20 volt over this, potential difference of 20 volt. Very simple JEE main type question. You are supposed to find the charge on this plate. This plus Q's value you have to find, nothing else. So you will be revising capacitance chapter from term one CBSE's perspective later on. But for now, we can focus on these questions. Okay, let me calculate it. Yeah, Vedant, that's not correct. Kittu, your answer is right. So Kittu, which method did you use? What did you do in this? No, here, that's not correct. Okay, fine, Kittu. That is also correct. Yeah, here, that's right. Yes, Aryan, that's correct. No, Dev, not right. Rahul, not correct. Some calculation mistake is there. Dev and Rahul in your answer. Okay, fine. Yeah, Vedant, correct. Dhruvi, not right. Pranshu, correct. Rakshita, not correct. Even this question has two methods of solving. If you guys have already got the answer through first one, you can try the other one also. The first method is separation of charge in direct ratio of capacitances. If you remember, for resistors, the rule was separation of current in inverse ratio of resistances. For capacitance, the ratio is the rule is opposite. And the second method is separation, not separation, I should say division of potential difference in inverse ratio of capacitance, of course, in series. What am I writing? Ratio of capacitances. Okay. The first method we can use first. This is how the capacitors were. So for this, what you need to do is, first of all, you need to find what is the charge coming out of this battery. 20 volt and the capacitance was 2163. Okay. 2163. What's the equivalent capacitance of the system? 6 by 5. Okay. Yeah, guys. So I am guessing you will be able to do it, and you guys are getting 6 by 5. I'll believe that. 6 by 5 microfarad. So what's the charge coming out of the battery? That is C into V, equivalent capacitance multiplied by voltage. So that is 6 by 5 of this, which comes out to be 54624 microcoulomb. Yeah. So 24 microcoulomb is coming out. So this 24 microcoulomb is going to go like this. Of course, through the over the first capacitor, it's 24 microcoulomb only. But now it's going to split. What is the ratio in which it is going to split? The capacitance, if you notice, left side is 1 and the right side is actually 2. 6 and 3 in series makes 2. So it will divide in the direct ratio, 1 is to 2. So two parts go on the other side. So can we see charge going in the other one is 2 by 3 of the original 24 microcoulomb. That makes it 16 microcoulomb. Okay. Yeah, guys. So it makes it 16. So yes, whatever charge is going in this branch, same will be there on the first capacitor also, and same will be there on the second capacitor also. In series, charge is same. So the answer is 16 microcoulomb. Have you guys tried through the other method also? I think most of you tried using the first one. Can you do the second one also? Okay, 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 Dara, great. Okay, okay, fine, great. Hmm. So it's a little bit lengthy. It is not the best method to do this question, but still we should know all the methods. So the first one is 2 microfarad. Other one is what? Like what is the equivalent capacitance of all these three? So it's going to be 3 microfarad, right? And the overall voltage you're giving is 20. Like I'm saying, all these three combined are 3 microfarad. So in the inverse ratio, the potential is going to divide. Like ratio of capacitance is 2 is to 3. So potential divide 3 is to 2. So you can imagine 2/5 comes on it. 2/5 comes on it, right? I guess so. Yeah. 2/5 of 20 volt comes on it. That is 8 volt. Yeah, 8 volt. Now, which 2 points is 8 volt coming over? This point and this point, which in the original figure is this point and this point. That basically means this is a very important point. This means this capacitor has 8 volt present over here, and both these capacitors have 8 volt pressure over them. Is that fine? But now this 8 volt will further split into two parts. This 8 volt is over these two capacitors. So what will be the potential difference over this other capacitor? Which one is supposed to be 3 microfarad? Yeah. Over this one, what is going to be the potential? Can we say that is going to be inverse ratio? 2:1 is the ratio. So 1:2. 2/3 of 8 volt, 16/3 volts will be present over this capacitor. That is also fine, but I want to teach this method. That is, I'm doing it. Yes, Anshu. In fact, better than that is using the first method itself. So guys, voltage over this one is going to be 16/3. You know the capacitance. So charge over this one is going to be 3 microfarad multiplied by 16/3 volts. That is 15 microcoulomb, the same answer. Now what I did was I divide this 20 volt into this and this combination, and then further split this 8 volt in both of these. That's how you can do it. Okay, guys. So rest will continue the next time. What you guys can do is you practice questions from this, particularly focusing on JE exercises. Okay, if you feel confident in today's class in any topic, then it's fine. Go for JE exercises. If you feel a little bit inconfident, you can go for state level for now. Okay, if you are feeling inconfident, because state level exercises are going to help you for term 1 preparation also, but only if you're confident, move to JE. Okay, if you're already confident, don't go for state. Okay, fine. See you the next time then. Okay, guys. Bye bye.